Okay,
No.
Facebook.
We are going to do these non-live videos.
Why?
Wait, so
You get a lot of likes.
Wait, is this stuff gonna be like a chemistry teacher?
Probably not.
Then
Miss
we're
Silverman.
gonna fail the class.
No.
It's going to be too relaxed.
Miss
How much
Silverman.
damage can they do?
Should be honest.
Okay, so I want to do some of the worksheet together with you guys. You guys have this worksheet?
Yeah.
Okay, so if you look at your learning targets,
Congratulations, Principal.
it says, I can use the periodic table as a model to predict the relative properties of elements based on the patterns of electrons. So what we're starting out with is we're trying to figure out how are these electrons arranged, and then from that we can get some information about what types of properties they're going to have. Okay? So on the first side of this element composition worksheet, first side of this one. I did want you to do it for homework, but I'm looking around and I see a lot of blanks. What about the other side? What does it say? Nice! Jason.
Yeah.
Jason, the man. All right. So Jason's going to have the benefit of
But I don't know what that is.
He's going to have the benefit of following along with his work, so he won't have to spend quite as much time reviewing the video tonight to actually make more meaning out of this. Okay? In the video, I explained how to do this first section, what's called an orbital diagram. We're going to try to show how are the electrons arranged. Now, the electrons are not in the nice little rings like we saw in the Bohr model. Okay? It's a little bit more complicated than that. They're still divided into groups, but not in quite the same way as the rings. Okay? So fluorine, when we write its orbital diagram, when we write its configuration of electrons, how many electrons are we going to have to represent for fluorine? If you don't have a periodic table out right now, you better get one out. How many? 9. Anytime we're putting electrons into an atom, where do we put them first?
First ring.
Well, we're not doing rings anymore. We're doing orbitals. The first orbital, we give it the name 1s.
Oh yeah.
Okay? So, unfortunately, we don't have enough time for me to fully explain where this comes from. So if you're curious, you take AP Chemistry and all will be revealed. Okay? So the 1s, what does it look like? Well, we don't actually know. We're just going to represent it with a box. All we're doing is representing where these electrons live. Okay, this is not, it doesn't actually look like a box around the nucleus. Okay, this is just a diagram to represent it. Okay, now what do I put in the box? I put little arrows to represent the electrons. How many arrows fit in a box? 2. And they only do it if they're going head to tail, or head to feet.
Can we opposite?
Head to head?
No, can we opposite?
Oh, you could put the first one down and the second one up. That's fine. As long as one is pointing up and one is pointing down. Okay? Now, the other way we represent this, sometimes we don't draw these boxes at all. Sometimes we just write 1s2. That 2 up above there shows us there's 2 electrons in this 1s position. It's kind of like that first ring, the closest ring to the nucleus. Okay, but this diagram is now representing fluorine. Who is this representing? Helium. Why do you say helium? We've only represented 2 electrons, right? So this can't be fluorine, this is helium. We've got 7 more to go. Where do we put them after we fill up the 1s?
2s.
The 2s. Now, I started to explain this on the video, but I didn't really follow through. On the periodic table, if you forget this ordering of what comes when, the periodic table is actually a good way to help you remember. If you look at your periodic table, it's actually split up into a couple of different chunks, or blocks, if you will. Now you do have to remember what block is what. This is called the S block here. On the far right is called the P block. In the middle is called the D block. And this chunk that we put down in the bottom in no man's land, that's called the F block. Now we're not even going to deal with F's. We're not even going to deal with D's. We're really just going to start off with the very top of the periodic table. We'll learn how to do the bottom of the periodic table in AP Chemistry. All right? But the rows are sort of like the rings, right? We start with the first ring, we start with the first row. So this is the first row, and when we go across in the first row, we're in the S block. Remember, I moved helium over here. Helium normally sits over here, but I stuck it in here, okay? So in the first row, the only thing we hit is an S. We go across, there's nothing in the D, there's nothing in the P, so we're never going to write a 1D or a 1P. It doesn't exist. Okay? After we've filled up that 1S, now we go into the second row, which is analogous to the second ring in the Bohr model. The first thing we hit is in the S block, so we're going to call it the 2S. That's what comes next. Okay? And actually, if you look at that S block, how many elements wide is this little chunk of the periodic table? 2. That's a good way to remember that the biggest number we're going to write here after an S is 2. The number of electrons that can fit into that space equals the number of elements wide that block is on the periodic table. That's just a way to remember it. But memorization works as well, just straight up memorizing. Okay? So for fluorine, how many is it going to have in its 2S? 2. It's got to fill it up. We got more to go. We got to fill up the 2S. 2S is filled. How many more do we have to represent? 5 more, right? We've represented 2 plus 2, 4, but we got to get to 9. So we got 5 more to go. Where do we put them after the 2S? 2P. The 2P. The apartment building. Which has how many apartments?
3.
3. Right? Now, in those 3 apartments, how many electrons can we fit total?
6.
6 total. 2 in each apartment, right?
Yep.
But does fluorine need to totally fill it up?
No.
No, because we're only trying to get to 9, right? If we're already at 4, and I put in 5, 6, 7, right? Everybody gets their own apartment until we have to. Now we can start to pair up, right? But again, right here I'm only at 7. I'm trying to get to 9. So here's my 8, and here's my 9. So since I've only written 5 electrons in the 2p, I'll put 2p5 there. Okay? Cool. So that's what's going in the orbital diagram for fluorine. Now it's asking you in the next column to say how many valence electrons does it have. So we have to define valence electrons. Those are the electrons in the outermost furthest from the nucleus and I'll put or highest numbered orbitals. Now after you write that definition, I'm going to explain what it means. So in your notes, I'd be writing that definition. Electrons furthest from the nucleus. When chemical reactions happen, it's only the outermost electrons that are involved. We're not going to start messing with the electrons in the first ring if we've got electrons in the 5th ring. The 5th ring, they're the outermost, they're the easiest to play around with. Okay? I put the highest numbered. What do I mean by the highest numbered orbitals?
1, 2, 3.
Yeah, I mean the numbers in front. I don't mean how many electrons are in there. I mean what is the number that's out in front of this thing, right? So a 2s is a higher numbered orbital than a 1s. Okay, so for the sake of fluorine, our valence here, since we have 2's in front of the s and in front of the p, those are both my valence orbitals. If I was talking about an element that had 3s and 3p electrons, the 2s and 2p are not going to be its valence, right? It's whatever ones have the highest numbers in front of them. Does that make sense? Question?
Wouldn't it be 3p?
No, because the second row, we actually have something going on in the p block here. So it's actually the 2p that comes up to the 2s. When we go into the third row, in the third row, we hit a 3s, then we go across, and then we hit the 3p.
Okay.
So the 3p would fill after we've totally filled up the 3s.
Why isn't it 3p?
Why isn't what 3p?
The fifth?
I guess the analogy would be like, remember when we did the Bohr model? The first ring could hold 2, the second ring could hold 8. In this model, we're saying, well, the second ring is actually split up into 2 chunks. It's split up into a 2s and a 2p, the 2s holding 2 and the 2p holding 6. That's where we get our 8, like in the Bohr model. Okay? But yeah, these are both analogous to the second ring, which is why they have 2's in front of them. Great question. Okay, so it asks the number of electrons, number of valence electrons. How many electrons are in our valence orbitals? 7. So we have seven valence electrons in fluorine. Then I say electrons gained or lost to have 8 valence electrons and be like a noble gas. So in the video I talked about noble gases. Why do we call them noble gases? Come on. Why do we call them noble gases? What's the word noble mean? Like what? No. Like nobility? If you're a member of the nobility?
Like you in it.
In what? Such a noble creature.
Does it exist?
No.
Like great?
Great. Nobility would refer to kings and queens, right? Nobles.
Oh, special.
Special, yes.
Royal.
What's special about these elements here that we call the noble gases?
Oh, it doesn't go to the...
Dirks?
They don't mix with others. They don't like mix with others.
They don't have to even deal with other elements. Helium's like, you know what? I'm good. I got just the number of electrons I need. I'm not going to have to ask for electrons from some other peasant. I'm not going to give up my electrons to somebody else. I got what I need. Okay? These are noble because they do not react. The reason they don't react is they actually, when we draw their configurations, they're completely filled. They've got all their boxes filled. And that's what makes an element stable, chemically. Okay, we talked about nuclear stability in terms of needing about the same number of protons and neutrons. Here we're talking about chemical stability. Okay, so if I had fluorine atoms in the room, if I just let out a bunch of fluorine atoms into the room, what's going to happen? Well, they're trying to be like a noble gas. Is fluorine like a noble gas? No. Not yet. The nearest noble gas to fluorine is neon. Neon has 10 electrons. Neon would have one more electron here and it would completely fill up its 2p. Right? If it had one more electron and filled the 2p, then its valence shell would be completely filled. So fluorine wants to do that as well. How can fluorine fill up its valence shell? It needs to gain an electron.
And that would be a noble gas.
It won't really be a noble gas.
Like, wait, so a noble gas is it?
It will be like a noble gas. Why is it not actually turning into neon?
It doesn't have enough protons.
Didn't change its number of protons. Still got 9 protons, so it's still fluorine, but now it's got 10 electrons, so it's like neon in terms of its distribution of electrons, which is going to make it more stable. But it's not actually becoming neon, it's becoming what?
Like neon.
Like neon. What's our word for an element that has gained or lost electrons?
Ion.
It's become an ion. Okay? Question.
Wait, what's a noble gas again?
Anything on the very farthest right column of the periodic table. Helium, neon, argon, krypton, xenon, and radon.
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 Random.
Yep.
Okay, so what is the symbol for the ion that
Radon
fluorine
right
is
there.
going to form? We put a -1 here. Okay, so for this unit, we're not really interested in the mass number or the atomic number, okay? Unless you're not sure why we got -1. Remember the charge, what was our definition of charge?
Number of protons.
Electron.
Protons minus electrons. So yes, if you want to know why this is a -1, you have to realize that fluorine has 9 protons. And now to fill up its valence shell, it's going to have 10 electrons. 9 minus 10, -1. That's its charge, okay? You can also remember if electrons are negatively charged, this is telling us we have one more negative charge than we have positive charge. We have one more electron than we have protons in this ion. John,
Here's the back one.
please do. Okay? Now, take out your learning targets. Corbin, read the second, well, actually the first non-bold one in that first group.
I agree with the periodic table to identify the significant regions or groups. Metals, non-metals, non-metals, alkaline earth metals, transition metals, halogens, and
Woo! That's a lot of crap to memorize, okay? The most important one, the one I want you to circle right now, is the last one he read. Noble gases. Circle it and then write a little note there to tell you where are the noble gases. Farthest right. Last column. Okay? Noble gases are the most important because that's what everybody's trying to be like in terms of their configuration of electrons. Okay? Tasneem, read the next one.
I can recognize that elements in the same group have similar properties.
Okay, this one is extremely important. I can recognize that elements in the same group have similar properties. Now, above the word group, I want you to write another word. Column. On the periodic table, groups are these columns. The vertical lists of elements, right? So the noble gas group is this column of elements at the very end of the periodic table. Okay? Now it's saying that elements in the same group or the same column have similar properties. So we just found through looking at the configuration of electrons that fluorine is going to form a -1 charge ion. Well, chlorine's in the same group. What charge do you suppose chlorine ions are going to take? -1. What charge do you suppose bromines are going to take? -1. Iodine? -1. Astatine? -1. So at the very top of your periodic table that's in front of you, on top of that column, I want you to write -1. And I'm going to show you why right now. I didn't ask you to do this one. So at the very bottom of your yellow worksheet, the one that we're working on here, there's just enough space for another one. Let's write chlorine here at the very bottom. We'll do chlorine together. How many electrons in chlorine?
Please come back here.
How many? 17. Where do we put them first?
1s.
1s. How many are in there?
2.
2. We got to fill it up. What fills after the 1s? 2s. How many's it got in there? 2. Fill it up. What's after 2s?
2p.
2p. How many boxes?
3.
2 in each box. We got to fill this one up too, right? Okay. Is the 2s and the 2p our valence orbitals? Not for chlorine, because we've only represented here 2, 4, 10 electrons. We've got to get to 17. So who's going to fill after 2p? 3s. We're going to go into that third ring, which is actually split up into 3s. And the 3s has got to be filled for chlorine. How many are we at? 2, 4, 10, 12. We got 5 more. Where am I going to put them? 3p. The apartment. And the third ring is actually an apartment and a single family home. So how many do I need to put in here?
5.
5 to get to 17. So 1 in each apartment, but we got to get to 5, so we're going to have to double up 2 of the apartments. Does that make sense?
What's the valence?
Which ones are the valence orbitals for chlorine?
3s, 3p.
The 3s and the 3p, the ones with the biggest numbers out front. So these are the valence. And how many do we have in there?
6, 7.
7. Now, chlorine wants to be like a noble gas. Who's the closest noble gas to chlorine?
AR.
Argon. How can chlorine be like argon?
16 minus 17.
You can do what?
Add 1 electron.
Add 1 electron. If you look at its configuration, look, it's got 1 spot. Just needs that 1 more electron and it'll be completely filled for all of its valence and all of its other boxes as well. So if it just gains 1 more, it'll have the same configuration as a noble gas, like argon, and it will be stable. So chlorine gaining 1 will also form a -1 charge. Okay, so that's why I think we're okay in putting at the very top of this column -1. Any element, if you're to do this, to write out these configurations, any element in this column, you're going to see is 1 short of being like a noble gas. So they're all going to gain 1 electron. Cool?
Does that mean the next row over is going to be too short?
Yeah. Think about the pattern. These are all going to be too short, right? Oxygen is going to need to gain 2 electrons to be like neon. So if you want, above oxygen's column, you can write -2.
And then -3.
Then -3, yes, if the pattern continues.
Until B.
Now wait a minute.
Do you have any extra periodic tables?
Oh yeah.
I think I lost my guess.
Actually, no. I got some I could loan you. I'm going to print everybody a new periodic table for tomorrow. So you can borrow one for today, but it's a laminated one.
Wait, what's tomorrow?
Tomorrow I'm going to print you the periodic table that's going to look exactly like the one you're going to get on the final exam. And then there's some information on the back that you're going to need.
Wait,
Yours don't have a back to them, do they? Does anybody have stuff on the back of theirs? A few people do, but most people don't. So I'm going to print you a new one for tomorrow.
wait, this one.
We'll talk about what we need tomorrow.
Does it stop until B?
Okay, carbon we're going to wait on for a second. Don't put anything above carbon's group. Okay. I want to do another one of the examples from your worksheet. Let's do the third one, magnesium. Let's write the configuration for magnesium. Everybody good with this fluorine example?
Yeah.
Okay. Dirks! Magnesium. What's it got?
12.
12 electrons. Where are we going to put them? Come on.
1s.
We're going to start in the 1s. We always start in the 1s. How many does magnesium have in there?
2.
2. Got to fill it up. Next.
2s.
2s. How many is magnesium? They needed 2 of them in there for magnesium. Next.
2p.
2p.
3 boxes.
3 boxes to represent it.
All of them.
Fill it up. Fill it up. That's only going to get us to 10. We got to get all the way to 12, right?
3s.
Okay. After that comes the 3s. And if we put 2 in there, that represents magnesium.
Wait, one question. Is there anything after 3p?
Yes.
4p.
I just erased that periodic table, but after you get all the way across on the 3rd row, you go to the next row.
Oh.
The 4th row, you'll hit a 4s. Okay? Now, we're not going to deal with anything after that. 3p is as high as you'll have to go for this class, because it gets a little weird after that. There's a reason it gets weird, but I don't want to talk about that until you take AP chemistry.
Wait, when do we take it?
You would take it probably your senior year. Next year, you're going to take some form of physics. If you're doing really well in chemistry, you're going to challenge yourself by taking AP physics, which sounds scary, but it's really just honors physics with 1 more unit than what we used to have in our honors, so we get to call it AP. So if you want to challenge yourself, take an AP class your junior year. You might get college credit, even if you're not going to be a science major. You might knock out your entire science requirement in 1 year, one slightly painful year of high school physics. And then, if you get that experience, then you can bump up and try to take AP chemistry.
Do we have to take AP chemistry?
Some of you do, because if you don't, you're going to make me sad.
I'm not.
You got a lot of work to do before I get sad about you not taking AP chemistry.
Wait, why don't we jump from chemistry to physics back to chemistry?
Well, your senior year, you could take a whole bunch of stuff. You could take AP Environmental Science, you could take AP Biology if you really liked biology, you could take Anatomy and Physiology if you want to learn about the human body, you could take a Health Careers, you got all kinds of options your senior year. But of course, you're going to want to come back to your favorite teacher, Mr. Bull. Your only other option is AP Chemistry. Okay, so back to magnesium. 1s2, 2s2, 2p6, 3s2. What are magnesium's valence orbitals?
Is it only
3s.
It's only the 3s, right?
Yes.
Every time you see me,
So it's got 2 valence electrons. Now, the question is, how is magnesium going to become like a noble gas? John?
by adding. Wait, magnesium is. What is that? Mg? Oh, it's
It's not a noble gas.
Yeah, but
Look at where magnesium is. It's not in the noble gas column. It's got to get all the way over to here.
so
It could add 6. Where would it add them to?
The 3.
The 3p, right? The 3p in normal magnesium is not filled, agreed?
yeah,
But remember when we did the flame test lab?
yeah,
What was causing those colors?
oxygen. No, no.
We had a bunch of different elements. We put lithium in there, we put strontium in there. What was happening to the atoms to make them give off those colors?
Burned up.
Combustion.
Didn't we see a simulation with a little electron going around,
Shaking.
and then it jumped to a bigger orbit, and then it jumped back down to a smaller orbit, and those jumps are responsible for the colors that we saw. Okay, now it's a little bit more complicated than that, but we can take an electron from, say, the 2s, and if we put it in the flame, it might jump up to that empty 3p. Then when it jumps back, it's going to give off a certain color of light that we're going to see through our little spectroscope. Okay, so actually magnesium, even though it's only filling up these, it's got all the other ones that are empty, all the way up to 5p's and 6p's and 7p's. That if we put magnesium in the flame of a Bunsen burner, we might excite those electrons up. But this is where they're normally going to live. Okay, yes, you could do an Airbnb and move yourself up to the penthouse, 5p, something like that, but you're not going to stay there forever. You're going to stay there one night, you're going to drop back down, and when elements drop back down, they give off light.
Airbnbs are nice.
I know.
Have you done one?
Yes, magnesium could gain 6 electrons, and then it would completely fill up its valence shell. But there's an easier way.
You lose,
If magnesium never had these electrons,
then it'd be closer.
then its valence would actually be the 2s and the 2p.
Oh.
And look, its 2s and 2p are filled.
Wait, can we subtract them?
Well, we don't really subtract them, we just get rid of them.
Yeah.
So magnesium, if we think about like the landlord analogy, it's like, hey, you're evicted, get out of here. Find somewhere else to live. I'm about to bulldoze this 3s. Okay? Now, where are these electrons actually going to go?
To the 3p. No.
No, these are already filled. We don't want to put them up here, we want to totally get rid of them.
You're gonna shoot out, I don't know.
They're going to go to another atom. Remember chlorine needed to gain an electron?
Yeah.
Oh, it's still it.
It's not going to steal it. Magnesium's giving them away,
Go.
right? Magnesium's like, I got electrons to give up. Who wants them? Who wants them? Chlorine's like, me. I need one more. I just need one more. Magnesium, come on. Okay, so when we talk about ionic bonding, one element is getting rid of its electrons, the other element is trying to gain electrons, and that's what makes both those elements more stable. Okay, so we'll talk more about that in a minute. Question?
Wait, so does that mean we have to change this one too? To, like, you know how you said 3 is the last one? Like, for Mg3 as for valence?
Well, you're asking about the fluorine example?
No, for this one. You know how you said...
So I asked you to write the neutral one first.
Oh,
Okay. But now what I'm explaining is that in order for magnesium, yes, magnesium has 2 valence electrons. That's the next column, right? Number of valence electrons is 2. But then it says electrons gained or lost to have 8 valence electrons and be like a noble gas. Our first pass, we said, well, let's gain 6. Let's become a -6 ion. But I'm saying there's an easier way. Because we're forgetting that magnesium's actually closer to being like neon than it is to being like argon, right? Neon's got 10, magnesium's got 12. So it's easier just to lose those 2 and be like neon than it is to gain 6 and be like argon.
So
Okay?
on the test, if you added 6, would it be 1?
Yes. You will probably get some partial credit because at least you're thinking about, like, you know,
Getting there.
they're trying to fill up their valence shell, but in reality, for magnesium, it's easier for magnesium to give up 2, and if it gives up 2 negative charges, it'll still have 12 protons being positively charged, but now it'll only have 10 electrons negatively charged, so it'll be a +2 overall charge. Does that make sense, Jim? Cool. Okay. So now you could even say that its new valence shell, or new valence orbitals, are the 2s and the 2p, and those are filled now, right? So now we're saying this is now a stable ion because its outermost set of orbitals, the outermost places where electrons can live, it's all completely filled up. So that makes it like a noble gas. This is like the noble gas neon. It's not actually becoming neon, it's becoming an ion of magnesium. Just
Wait, so for the, we look at the valence number of electrons to get to the noble gases?
essentially. Well, they're trying to get to 8, but what I'm saying is magnesium's a little tricky. Normally it has 2, but it's actually easier to lose those 2, and now its new valence, it'll be 8, than for it to gain 6 to get to 8. So it's a little bit tricky. A better shortcut would just be, what does it need to gain or lose to be like a noble gas? Okay? Now this is the actual reason. Whether you memorize this reason or not is not going to matter for the final exam. For the final exam, all you're going to have to do is figure out the ion. Now for us, we're going to write at the very top of our periodic table in the column that contains magnesium, which is the second column. Up here we're going to write +2. Why?
That's what you need to do to have it be a noble gas.
But is that going to be the same for calcium?
No.
Yes.
Yeah, it-
Oh, yeah.
Everything in this group is going to behave
I
in
thought
a
you meant-
similar fashion. That's what that learning target is talking
I
about.
thought you
I
meant-
can recognize that elements in the same group have similar properties. One of the properties that's similar is their charge. Everything in magnesium's column is going to take a +2 charge.
You can't jump
And
rows.
then
though,
hydrogen is
You
1.
can't what?
right? You can't jump rows though, right?
Well,
You
rows are these.
Like you can't. Like you know how.
No, you can't jump columns and say sodium's going to have the same charge as magnesium. It's just this column that forms +2s.
Is it going to be +1? Not for hydrogen.
Hydrogen, lithium, sodium, potassium, rubidium, yeah, they're going to be +1. If we think about lithium, lithium's got 3 electrons. The easiest way for lithium to become like a noble gas is not to gain 7 and be like neon, it's to lose 1 and be like helium. Okay, so put a big +1 above hydrogen's column on your periodic table. Okay? Now, I said we were going to forget about carbon for a minute. Why? Carbon's actually at a position where it's got 4 valence electrons. So it could gain 4 to be like a noble gas and to get to 8, or it could lose those 4. So carbon's group, we write +or -4 above it. It can gain 4 or it can lose 4, it depends who it's with. All right. Boron, on the other hand, that group is always going to be a +3.
Isn't it only one?
Wait,
Huh?
so
Is it only one?
Boron, aluminum, gallium, indium,
Oh yeah.
and thallium, that entire group are going to form +3 ion. Doesn't-
the number of valence electrons, would it just stay 2?
No.
Would it
In
change?
magnesium 2+, it'll have 8 valence electrons. Because the new valence ones are the 2s and the 2p.
So what kind of charge would helium?
What kind of charge is the noble gas is going to take?
0?
0. They don't form any ions. They don't need to gain or lose. They're already good to go. So yeah, if you want to, just to remind yourself, you could put a 0 above the noble gas column. They never gain or lose electrons. They're all set. Okay. So I'll leave it up to you guys to finish the front of that. But let's look at the back for a second. Nope. I'm going to put up the answers in about 10 minutes. Okay. But on the back, this is very similar to that worksheet that we did on element composition, when we were learning how to do the protons, neutrons, electrons, atomic number, and mass number, right? But now we're not really worried about the neutrons. All we're worried about is the protons and electrons. We're worried about the charge. We want to know, is this going to form a positive ion or a negative ion? So let's do the first one together, lithium. What's lithium's atomic number? 3. What does the atomic number tell us? Number of protons. So the protons column for lithium, you're going to fill in 3. Okay, what's next?
2 electrons.
We got to figure out the number of electrons. How do we figure it out?
The charge.
From the charge. So this can be a little bit tricky.
Protons minus electrons.
Protons minus electrons. So if you want to set up an equation here, you want to say the charge equals protons minus electrons. Well, for lithium, we know the charge is +1. We know it has 3 protons, so we can solve for E, the number of electrons. If we remember algebra. How are we going to do it? Subtract what?
-3.
All right, subtract 3 from both sides. Make it hard on yourselves.
Right.
We get -2 is equal to -E. Now what?
Divide by
-1.
each other.
Divide both sides by -1. So the number of electrons is 2. Okay.
More work.
The other way to think about it is to say, well, if it's +1 charge, it has to have 1 more proton than it has electrons, right? If it has 3 protons, it's got to have 2 electrons, yeah? Okay, now the next column says difference between the positive and the negatives.
1.
+1, right? There's 1 more positive than it has negative. That's just to reinforce the idea that this is not telling you that it has 1 more electron. It's telling you it has 1 more positive charge in it than it has negative charge. Okay? Very important to keep in mind. So now we got 2 words. Cation and anion. I know. It looks like cation, like ration, right? But it's cation. Because it comes from the word cathode and anode, which are 2 of the terminals of a battery. Cathode and the anode. Okay? Cation, what's the charge on a cation? Positive. How do you remember cations are positive? Cats have paws. Cats are positive. Cations are positive ions. Or, if that's too cheesy for you, you can remember that that T looks like a plus. So cations are positive. It doesn't look like a plus. It looks more like a plus than any of the letters in this word.
No, really.
So yes, that might not be helpful to you. That's the way my crazy brain works. I remember a T looks kind of like a plus, and so cations are positively charged. All right, let's do a couple more together, and then we'll take a quick break.
Wait, how do you remember it?
Anions, I remember it because, well, somebody last period said anion looks like onions. Onions make you cry. That's negative.
Oh
Okay.
my God.
I remember it because anion has 2 N's in it. Negative. It's got an extra N in it. It's negatively charged ion. Okay? It's just, you just got to come up with some way to remember it. But yeah, it's just memorization. What? Lithium is a cation. Yes, that's the last column. Okay? All right. Let's do this one together. What the heck? They don't even tell us what element it is.
7.
Sevenium?
No.
Nitrogen.
Ah, if the proton's a 7, the atomic number's 7, so it's got to be
Nitrogen.
nitrogen. Okay, but now we got to figure out what ion of nitrogen is this. How do you know it's -3? Yeah, we've got 7 protons, 10 electrons. We have more negatives than positives. We have 3 more negatives than positives, so it's nitrogen -3. Okay, so is it a cation or an anion? anion. It's a negatively charged ion. It's an anion. Okay, now I want to do, give it just a second to finish that. I want to do this one.
Which one?
Iron.
Oh.
Iron 3? Everybody find iron on a periodic table. How many electrons does iron have? 26. 26 protons, 26 electrons when it's neutral. To be like a noble gas, iron would have to do what? It could lose 8 and be like argon. It could gain 10 and be like krypton. 26 plus. Okay? It turns out it does neither. It does not gain 10 or lose 8. It loses 3. Sometimes. Sometimes it loses 2. This group in the middle here, from scandium to zinc and everything below, this little low block right here, these are called transition metals. That's actually one of the sections in this first learning targets. Transition metals, halogens and then noble gases. Transition metals are in the middle of the periodic table. Transition metals are weird because they form several different ions. So it's not as simple as like what we did with chlorine, where we just said, okay, it has this number, it needs one more to fill it up. Transition metals are weird. What are you doing with all my markers? For transition metals, I will tell you the charge.
Okay.
That's the charge.
3.
That's a Roman numeral, right? So, who knows the Roman numerals?
Not me.
I know like 1 to 10.
I just
1
know
to 10, that's all you need. Actually, 1 to 5 will probably do you.
I just know.
Yeah, I know 1 to 5.
I know
It's I is 1, 2 is 2 I's, 3 is 3
So
I's,
I is
4 is
the Arabic
IV, 5
numeral.
is V.
Yeah, that's an Arabic.
I learned that from GTA.
Yes. I in Roman numerals corresponds to the Arabic numeral 1.
It
It is.
is.
Okay, that's the word. But don't they look like this? Do they not look like this in Arabic?
No.
Well, it's like number 1.
Only number 1.
A 2 doesn't look like this in Arabic?
No.
Looks like looks like opposite 7.
Weird. Why do we call them Arabic numerals?
I don't know. I don't even know.
That's
That's a
numeral.
fantastic question. But
That's a
we do
numeral.
call them Arabic numerals. Our Western sort of 1, 2, 3, 4, those are Arabic numerals.
Maybe because someone
Now,
from like
what this really means, what we really care about is what is the charge. If you see a Roman numeral 1 next to a transition metal, its charge is +1.
neutral. Okay.
How'd you get a negative?
Oh yeah.
Just have a negative.
No transition metal will ever form a negative. They're always positive.
Oh.
What's the Roman numeral for 2? I. How about 3? I. Okay, that's going to be a +2 and a +3. What about 4?
IV.
IV. Why IV?
Because it's 4.
Because 5 minus 1.
Yeah, 5 is V.
I just
If I
know
put a
this.
1 before the V, Romans knew that meant 1 less than 5,
I love GTA.
which was 4. Why wouldn't they put IIV for this?
That's 8.
It's 2 less than 5.
Oh wait. I thought it's
Right.
8.
I think that's more lines
it's
than just
VI.
writing III. Okay? 6 would be VI, 1 after 5, and 7
Yeah.
VII, right? But you're not going to need to read 7. What was your question? Okay. So, in this case, iron, I'm telling you it's iron +3. So, when you write the difference between positive and negative for iron 3, you're going to write +3. How many protons in iron? 26. So its atomic number?
26.
26. Now, if it has 26 protons,
23 electrons.
it has to have 23 electrons. Because it's positively 3 charged, right? So it has to have 3 more protons than electrons, so it can only have 23 electrons.
Is it cation?
It's a cation, yes. Cation. Okay? So we should be able to finish the rest of this. Here, guys, the most likely ion, that's where we're going to use the very top of the periodic table, those charges that we wrote. We have to start memorizing what charges certain columns are going to
Wait,
take.
we didn't write that.
So
We didn't write it for oxygen's column?
Oxygen's -2.
Yeah, this column is -2.
Also,
What
for
about
that,
nitrogen?
Well, I did.
most likely ion
Ionic
of
normal is
oxygen
three numbers.
-3. Okay, so as you guys are finishing this up and taking a quick break, I'm going to look up the etymology of aerotropical.
It's like this.
Most likely ion of oxygen is -2, right? Or am I just whipping it down?